FPN channel. Here I will try to give you some useful information about the polyurethane industry. Today I would like to talk about a little bit polyurethane chemistry. Polyurethane chemistry is all about the reaction between NCO and hydroxyl group in presence of a catalyst, which gives urethane. This reaction is called gel reaction. From the second reaction is between NCO and water molecule, and also in presence of a catalyst. And the result products will be urea and CO2 gas. This reaction is called blow reaction. And we need gel catalyst for gel reaction and blow catalyst for blow reaction. So the gel reaction is used to produce, for example, the elastomers coating, but these two together, gel and blow reaction, we use it for production of, for example, flexible foam. And the CO2 gas is play a role like a blowing agent. And the blowing agent gives the cellular structure to the polymer matrix to produce foam. So the third and fourth reaction, which are side reactions, are reaction between NCO and urethane from one side and NCO and urea from other side. And the resultant products, side products, are olefenate and butyrate. These are side products that give some impact and some properties to the final product. For example, they give more hardness to the final polymer. So regarding the isocyanate types, we have aromatic isocyanate and we have aliphatic isocyanate. Aromatic isocyanate has two main products inside. One is MDI and the other one is TDI. MDI is methylene diphenyl diisocyanate, which have three different isomers. So we have 4,4 isomer, 2,4 isomer, and 2,2 isomer. So in 4,4 isomer, the NCO groups are located in the fourth position of the molecule. In 2,4 isomer, one NCO is located in the second position. The other one is located in the fourth position of the molecule. And the 2,2 isomer, which is not so important, and the amount is very low in the mixture, has both isocyanate are located in the second position. And the functionality for all three isomers is 2, and NCO is 33.5%. And the second part of the mixture is polymeric MDI. So polymeric MDI, as it is clear from the structure, is a polymer, not a small molecule. And the functionality is between 2 and 3. NCO is 31 to 32%. And the most used grades of polymeric MDI in the market is PM200. So it means that the viscosity of this product is 200. So these old products are being produced in the big and huge petrochemical complex in China, in America, in Europe, and so on. So they produce the mixture of all products together. And the companies, during the production, they separate different grades of isomers and sell it to to the targeted markets. For example, 4,4 isomer is called pure MDI, and it is solid at the room temperature. It is called mainly for shoe sole, flexible foam, and so on. The 2,4 isomer is not existed alone in the market, but it exists as a mixture with 4,4 isomers in different ratios. Depends on the application and requirements are needed. So as I said, 2,2 isomer is not so important, and the amount is very low in the mixture. So the polymeric MDI is being used in the production of rigid foam because of the higher functionality. So, for example, in sandwich panel production, refrigerator, and so on. And sometimes polymeric MDI is also used in the formulation of the isocyanate for flexible foam and case products. The second class of the aromatic isocyanate is called TDI. TDI has two grades in the market. TDI 80-20, which has 80% 2,4 isomers and 20% 2,6 isomers. And TDI 65-35, that 65% 2,4 isomers and 35% 2,6 isomers. The difference between the MDI and TDI, as we can see in the structure, molecular structure, the MDI has two and more benzene ring or aromatic ring in the structure, but TDI has just one aromatic ring. So it means that the product which produced with MDI will have more hardness than the TDI in the final product. So the aromatic isocyanate has a big disadvantages and weak point. Its weak point is their low resistance against the UV. So for example, when you want to produce a coating, outdoor coating, so it is not good for that application. That's why we need the second class of isocyanate called aliphatic isocyanates, which are very resistant against the UV. So in aliphatic isocyanate, we have two types. One is linear aliphatic, like hexamethylene diisocyanate, and we have cyclic structured isocyanate, aliphatic isocyanates. One is, for example, IPDI, isophorone diisocyanate, and the other one is HMDI, methylene dicyclohexane diisocyanate. So after the isocyanate types, we go to the polyol types. The polyol types, I would like to explain the two important class of polyol types. One is polyether polyol, the other one is polyester polyols. In polyether polyol, we have ethylene oxide, propylene oxide, and butylene oxide as monomers. But these two are very important in the industrial production, industrial use, to produce polyether polyol. And these polyether polyol are very good for flexible products like flexible foams, and they are good for low temperature application. For example, in shoe sole, for the low temperature application, you can use the polyether polyol as well. But the weak point of the polyether polyol is their low resistance against fire, against chemicals, and against oxidations. So because of that, we can go to the polyester polyol. In polyester polyol production, I would like to give some explanation. So in the production of polyester polyol, we use initiator and the monomers like ethylene oxide, propylene oxide alone or mixture based on because of the properties that we need. So initiator is very important. So if you use the initiator with two functionality, the final polyester polyol will have the two functionality polyol. So if you use the three functionality initiator like glycerin, so the final polyol also will have the three functionality. And even more, 4, 5, and so on. So when you want to choose the polyester polyol for some application, for example, if you want to produce flexible foam, you need the higher functionality, like 3. But in the elastomers and coatings, you need the 2 functionality polyester polyol. So you should put in mind that the selection of functionality of initiators vital for the production of polyester polyol. Regarding the polyester polyols, so we have diacid from one side and glycols like monoethylene glycol, diethylene glycol alone or as a mixture in presence of a catalyst, special catalyst, and heat. So you will have the polyester polyol and water. So as you can see, the reaction of the production of polyester polyol is a reversible reaction. What does it mean? It means that it can take place in both sides. You can produce it polyester polyol, and also you can produce again the reactants. So what should we do? We should remove the water molecule from the second side of the reaction to push the reaction in this side to produce polyester polyol, not the reactant again. So if we remove all of the water molecules from the system, then we will have mostly the polyester polyol with very low acidity, because the most acids are being consumed and the final acidity will drop dramatically. So the application of polyester polyol are mainly in shoe sole, in rigid foam, and sometimes in flexible foam in some special applications. Sometimes also in some applications we can use the combination, the mixtures of polyester and polyether polyol with the specific properties and the specification, like specific hydroxyl number, functionality, molecular weight, and so on, and acidity. So it means that the selection of the polyol, polyether, polyester, and also type of isocyanate are very important in designing practical and useful polyurethane systems for specific application. For now, this is end for this video, and thank you very much for watching this video. If you liked the video, please push the like button, and I hope see you in the next videos.